think we are live.
No, no sound. Okay.
Are you sure? Okay, now we're here.
So it was just lag, I guess. Yeah. Okay. Well, welcome everybody on this special occasion. As I guess most of you realized today is that the BVG tried their best to prevent us from coming here and having this event. But still, a few brave people came here, and the rest hopefully joins us at home in the live stream. So, yeah, so it's my pleasure today to welcome Robin. He's been an active participant here in the meetup since I joined it last year. So I'm really happy that today he will talk about functional reproducibility. That's actually a word that I frequently mistype. I don't know, there's I always put an A in there, I don't know why. But hopefully after today's talk, I don't do this anymore. So, Robin.
Hello everyone, I'm Robin, a freelance data engineer, data scientist. This is a topic close to my heart. I've taken quite a few sort of prototypes and put them into production. This is a kind of an evergreen theme for this sort of book. So what is reproducibility? Have you ever written the perfect program? Has it ever still run unchanged 6 months later? Can your colleagues run it without you? Just because your analysis is executable doesn't mean the results are reproducible. Data ages, libraries change, machines differ, servers go down, bits rot. Entropy is inescapable. This talk explains how to engineer reproducibility, drawing on techniques from functional programming and the MLOps movement. The code examples are designed for our audience, of course, but the lessons apply to any language. Physics tells us that energy can't be created or destroyed, but that doesn't make it an infinitely enduring resource. We can only use energy when we transform it from one form to another. We can turn chemical energy stored in coal into heat by burning it. Fire turns water into steam, which expands to drive pistons, becoming mechanical energy that we can use. We do work by transforming energy. But once the water has become steam and expanded, it can't expand again, unless it's first condensed by cooling. Though we've not lost any energy, we have created entropy. Entropy is energy that's not available to do work. In order to use energy, we need order in the universe. It's depicted on the left. We have an ordered division between a cold place A and a warm place B, or a hot place, I should say, B. Once we've made use of that difference and the energy evens out, now both places are nearly warm. It's depicted on the right. This picture shows a thought experiment. Maxwell's demon opens a door between two vessels, letting the faster gas molecules pass through and closing it just in time to keep the slower ones separated. In doing so, it appears to defy the second law of thermodynamics by creating order from disorder and reversing entropy. In an isolated system, absent any magical demons, while the amount of energy remains the same, entropy is always increasing. We can create pockets of order, but the overall trend is toward disorder. Decay is inevitable. Eventually, our universe will reach a state of complete disorder. a uniform, cold vacuum with no exploitable differences, the heat death of the universe. This is the way the world ends, not with a bang, with a whimper. Of course, we don't generally worry about this cosmic tragedy, and I'm not saying that we do the work that we do, attempting to bring order to data, is futile, far from it. This is merely a reminder we should not have the hubris to expect our programs to work forever, while our physical reality tends inexorably toward disorder. No one, not even the greatest engineers or scientists, are exempt. We do have reason for hope, though, not least because we have a tool that exists beyond the physical constraints of reality. The mathematics we use is pure and eternal. Functions are indefinitely reproducible. Here's the probability density function for the normal distribution. Don't need to worry about this every slide. Pi, an Euler's number, are constants, real constants. Given the same mean and standard deviation, this formula will always plot the same bell curve and always return the same probability density for any given value of x. This is all very well, but as beautiful as this formula is, it's not much use on its own. We can put maths to use by using R to plot density of the normal distribution. Here we use the default mean of 0 and standard deviation of 1, which gives us the standard normal, which are plotted between x of -3 and 3. In practical terms, we need to do computations to use maths, and computers are certainly subject to entropy. Computation sits on top of a whole stack of dependencies, from your code, through packages and programming language, down to machine instructions and the bare metal itself. None of this is perfect. Consider the tail of Leftpad. Not even a dozen lines of JavaScript was removed from NPM in 2016. It brought front-end development to a screeching halt as build failures cascaded across the web. Consider Gallery 404, a museum of obsolete digital art that was exhibited at the last Berlin Creative Code Challenge. None of these artworks are reproducible any longer. Servers go down, domains expire, Adobe Flash is long gone. The curator explained how some museums nowadays require digital art to be supplied along with working hardware, including backup systems, so that it can continue running over the longer term. So, how can we guard against this inevitable bit rot? How can we design and engineer our code to be more reproducible? Time to leave the metaphysics and consider some more practical guidance. As I alluded to earlier, we can turn to maths for help. And code manifests most directly in terms of functional programming. I'll explain some lessons from that approach, and then go on to describe ideas from software engineering that have found a home in the data world under neologisms like data ops or MLOps or model ops. And outside of the marketing hype, we can just think of this as rigorous data engineering. Let's start, though, with a question. Which of these statements are reproducible? Or rather, sorry, which of these statements are not reproducible? In fact, I don't ask the audience.
You say all.
Correct. None of them are. It's a trick question. Reproducibility requires that doing the same thing gives you the same result. None of these statements, even writing to disk, are reproducible. So let's explore why and what you can do about it. We saw the definition at the beginning, but what does it really mean to be reproducible? Pure functions are reproducible. The output of a pure function only depends on its input. The result doesn't change if it's calculated a second time or by another person. For the same input, you always get the same output. You could replace the function call with its return value in your program. This is known as referential transparency. Indeed, you could replace the function body with a lookup table that records the relevant output for each input. A pure function has no side effects. Running it doesn't change the state of the world. The only consequence is the output value it returns. Pure functions are idempotent, which means you can run them as many times as you like and always get the same result. Pure functions are composable. If you combine one pure function with another, then the result will also be pure. A pipeline composed of functions is much like one giant function. This is all very well in theory, but we can't continue piping data around in circles ad nauseum. At some point, we have to interact with the outside world to read a database, deploy websites, email reports. In practice, we need side effects. Side effects are intended consequences that happen outside of the function or the pipeline's output. We also use the term side effect to refer to causes that exist outside of the function or a pipeline's direct inputs. That is to say, non-local state. These side effects are what make our pipelines useful, allowing them to interact with the world. They're also what cause our pipelines to become non-reproducible. And it might be very obvious, this is the first time you're hearing this, so let's look at some examples. For the benefit of those who aren't familiar with R, most of this should be obvious. I should just point out this is the assignment operator, which for historical reasons is a bit idiosyncratic, but the rest looks like a lot of other modern languages. Here we see a side-effecting show count function. It implicitly depends on the counter variable that's defined in the global scope. This means that its result depends on the context in which it's run. Anytime you call show count, you could get a different result. It isn't reproducible. If the counter changes, then so does the result. The function has no return value. The call to cat, in this case, or it could just be print, is itself a side effect. In this case, a null is returned invisibly. And we can't use it in a reproducible pipeline. This might seem a bit contrived, but you could instead imagine the counter being a data frame that you're mutating in place. And similarly, if you depend on that in the global state, your function won't be reproducible. So let's refactor this into a pure function. We define describe count in terms of the count value. Now, dependency is always it is explicit. Given the same input, this function will always return the same output. It's reproducible. Indeed, it now returns an explicit output value reproducibly. The output is now data, not a side effect, so we can use it elsewhere. The call to print happens outside of the core logic of text entry.
A question from Barry. So he likes the example, and he wants to be a bit nitpicky, whether it's possible to use message instead of cat. But now you used also paste, so maybe...
It's also a side effect, so it doesn't change anything.
I didn't know about message, but thank you.
Yeah, for Barry, the message he wouldn't have thought about it as a side effect, but it's actually semantically it's the same, right? So it just prints something to the console. So
yeah, the distinction I'm seeking to make here is that previously we've got cat, which is both interpolating this value into the string together with lots of space in between, and also printing it out. It doesn't have any return values. returns null invisibly, which means it doesn't show you the null. Whereas here, I'm using paste because it's specifically showing the purpose of this function is to just join them, do the string interpolation. And the actual side effect of printing it out is then kept separate. It's in the same scope as the way the count is defined. I don't know what message does, so I couldn't speak to what how that applies here, but if it's doing the same.
He added that he meant the global variable lookup, but I don't get it. Let's continue. Maybe we can roll it up again later.
Yeah, so again, this is a bit contrived, but the same rationale motivates something like the brewing package, which extracts tabular data from trained models so that you can then manipulate the results programmatically and have access to the parameters and the code errors and standard errors and so forth. Where the base R summary method that is provided for something like an LM result only prints that table to the screen. So you can't use it then programmatically. It's a side effect of that method, not an output. So the code on this side, code on this slide has essentially the same functionality as before, but now it's reproducible. It's much easier to reason about. We've made the dependency on the context explicit, rather than implying on the global state. The focus of the function is on the value of the count, not the variable and its place in memory. And context mutations like this about value and its place in memory is exactly what happens when you reassign a variable or values within a data frame. And this example might look trivial, indeed it is trivial to help explain. But state mutation is a pernicious source of subtle bugs. Mutating states in place may yield savings in computer memory, but it imposes costs on human capacity to reason about the flow of data through your code as you try and keep a track of the running program in your mind. Pure functions operating on immutable data are reproducible, and you lose these guarantees once your pipeline has side effects and state mutations. Some side effects are not as obvious. The sample function depends not just on the arguments you pass it, but also the state of a random number generator. In software, the random number generator is not truly random, but rather a pseudo-random process. It gives highly erratic results, but follows a predictable process if you know the starting point. The starting state is seeded by some source that varies, such as the date, or a hardware source like dev-random, which collects noise from device drivers. This is a side effect for our function, causing its output to differ each time it's run. Indeed, each time I generate these slides, I get a different set of join classes. Although executable, this slide, and as a consequence the whole deck, isn't reproducible. We can make this function called reproducible by fixing in the initial state of the random number generator to a constant value with set seed. This level of purity might be helpful from an engineering perspective. For example, this slide has a consistent checksum, meaning it can be cached. But it would completely undermine certain analytical procedures. For example, in cross-validation, where we want to see the test train split vary to ensure we're not overfitting a statistical model. We forego reproducibility in resampling in an effort to achieve reproducibility on out-of-sample predictions. We might not always want perfect reproducibility. The key is in making that choice consciously. A more ubiquitous source of side effects is input-output. This doesn't just apply to third-party APIs or our database. Even the file system is non-local state as far as our program is concerned. It's not uncommon to see pipelines or notebooks start like this, with an absolute URI for the file system. And that file path is idiosyncratic. this code won't be reproducible on other people's machines unless they coincidentally have a user called Robin with this file in the home directory. Indeed, this probably won't be reproducible on my machine at a future date unless I take care to keep that file in place. More generally, even if that file path is dependable, there's no guarantee that the content of the CSV file itself will change. Even the writing of files is not reproducible. This function alone can't guarantee that the destination directory results exists. And these problems become all the more apparent with APIs or databases, where network interruptions and other external change can jeopardize the reproducibility of our program. The problem isn't that the side effects exist, they're necessary. The problem is that when they're implicit, they tend to hide dependencies. We can make them explicit with techniques like dependency injection. The function receives a database connection, for example, as an input instead of relying on it existing in the program's global state. Now the function declares its requirements. It draws attention to the potential side effects and forces us to think about them. Here we can see that get data will need us to manage the connections lifecycle rather than taking it for granted. The code is more modular. We can reuse this code within the same program, allowing us to get users from a test or staging database as well. Likewise, we can pull side effects through to the very edges of our pipelines, passing in state like data or configuration only from the outermost execution context. This means that the pipeline no longer has to be concerned with coordinating state. We may want some graceful error handling, but the pipeline itself should be context-free and reproducible. Indeed, extending this practice into the execution context itself is what leads to the infrastructure as code and DevOps movement, where machines and services can themselves be provisioned reproducibly from declarative configuration. Pursuing separation of these concerns, what Gary Bernhardt's called functional call imperative shell, leads us to a point where all of our dependencies are captured explicitly and their values gathered together in configuration. Here we have a pipeline composed of pure functions with all the necessary side effects contained to explicitly configured context at each end. It makes it easier to maintain reproducible code. When the code is changed, you can see how the pieces fit together and what the consequences of a refactoring are on the rest of the pipeline's code base. When the infrastructure changes, you may be lucky enough only to need to change the configuration and not the code at all. This also helps subdivide the code into well-factored modules, as each component explicitly declares its requirements, making them easier to test in isolation. The preceding example makes it trivial to pass in a test database connection. Well, no, this hasn't really solved the ultimate cause of our problems. As I explained at the outset, we shouldn't expect to ever be able to fix the rest of the universe in place. The best we can do is hope to contain the unreliable bits, pushing them to the edges so we can carve out the space to pursue reproducibility. A small domain where we, like Maxwell's demon, can reverse entropy and bring order to our world. We can go a step further and strive for reproducibility in our interaction with data outside of the pipeline. In these final slides, I'll discuss some lessons the data community can learn from software development, in particular, version control and continuous delivery. We've seen that the functional approach leads us to immutability, data that's unchanging. Steps in your pipeline can only communicate with one another through their arguments and return values. We aren't mutating the objects passing through the pipeline or the global state. The intermediate values are immutable. But we need to change things to do useful work over time as the external context changes. For example, as upstream data sources are updated. How do we cope when the upstream source is mutable? We can use versions to control external change. Versions identify immutable states of data as it evolves over time. What is a river? A place, some water. As you stand in a stream, you can feel the water flowing past your feet. You won't step into that same water ever again. Yet we think of that place as the river. You can't step in the same river twice. Time marches on. The river is formed of a different body of water, and you too will be a different person. Here's Heraclitus standing in a river. Different gallons of water flow around his feet. What's constant is the river bed. It's helpful for us to distinguish between the water and the riverbed. This is how we name rivers. The name refers to the riverbed, not the water that runs through it. We can apply this as a metaphor for data pipelines. We distinguish the output from each instance of it. Ultimately, the version is uniquely identified only by the values in the data. This becomes cumbersome, and we need a more succinct version identifier. Instead, we can identify versions by a name, formed of two parts. One is a location or a label we can use as a reference. The other is the version or a state in time. The outputs, the named output, and the versioned instances. You should certainly use version control tool like Git to manage your code and models. But line-by-line diffs and patches would be a very inefficient way to store data versions. The data, the parallel here isn't to source control, but to software releases. Data should be treated as an artifact, frozen in time. Artifact repositories will let you record provenance, for example, which version of the source or which of the run of the pipeline is responsible. You don't need a bespoke tool. Even a simple S3 bucket will let you update a key in place while it records the version history. Some databases support versioning natively, or you can create your own snapshots. This version history lets us retrieve the exact conditions for a pipeline run, so we can roll back and reproduce the results. Be wary of any upstream source that can mutate over time without providing some means of identifying and distinguishing versions. You can, of course, defend against this to an extent by keeping a track of the data you receive in caches or recording copies of API transactions in caches. But be a good data citizen and surface versioning information about your own outputs to downstream consumers so that they might ensure reproducibility in their work. Just because you can rerun your pipeline locally doesn't prove that it's reproducible. It's not demonstrably reproducible until it's running on ephemeral resources in a build system. A build system runs your workflow, recording the versions of the input data, source code, and output. The pipeline run itself is immutable and identified for posterity with a build number. Done correctly, we don't need to reproduce the pipeline. This contract serves as a guarantee you'll simply get the same result. This requires that the process of assembling your dependencies is automated and reproducible itself. No more hunting through messages or chasing colleagues to find that random Excel file that makes the pipeline work. You can't expect a build server to study the README and figure it out for themselves. Tacit knowledge must be explicitly codified. You can't claim that everything's fine just because it works on my machine. A build server is a shared consensus on configuration. A canonical source you can refer to see how things work. Automation enables collaboration. Building on an ephemeral stack further enforces the discipline by preventing you from relying on states. I'd argue that the success of containerization comes as much from virtualization as from the fact that Docker files, for example, automate dependency management down to the operating system level. Don't just say it's reproducible, prove it. Once you've versioned dependencies in an automated build system, you can develop continuously. A reproducible build enables continuous cycles, as it ensures you can always rebuild something from scratch, let it run idempotently, which is to say, repeatedly with the same effect. By having the discipline to avoid relying on state mutation, you can stop worrying about it. When you don't need to manage or even think about side effects, it's easy to cancel things, restart them, or even scale horizontally. It's easier to spin up concurrent compute resources. You don't need to coordinate state between them. When you can run a system continuously, you establish tighter feedback loops. You can understand the impact of changes sooner. Feedback loops help you iterate quickly and catch issues before they turn into bugs. Repeated execution encourages us to streamline our architecture, helping us become more efficient and reduce costs. Continuously exercising and testing your system helps to ensure reliability by giving weakness no space to hide. There's an overwhelming choice of continuous integration and continuous deployment tools, CI/CD, for software development like GitHub Actions and Travis or Jenkins, etc. And there's also tools and workflow systems specific to data and model development, like Apache Airflow. In closing, I'd like to urge a note of caution about the use of Jupyter notebooks. They are effective for exploratory work, but I found them to discourage reproducible data analysis. I should start by saying that exploratory data analysis doesn't need to be reproducible. We should have the freedom to explore data interactively to build up our understanding. We should expect to encounter dead ends. We should be prepared to throw away code. This is where REPL-driven development shines. So in RStudio, or Emacs, or VS Code, or any other number of IDEs, we have two windows. One to edit the code here on the left, and then another to run it on the right. You send the code from the editor to the console in a read, evaluate, print loop. The code is read and then evaluated by our interpreter, with the result printed in line in the console. And then we loop back to the prompt where for more input. The REPL lets us write code experimentally. We can execute each line to confirm it works as intended. You can tweak the code in the REPL console until you've got it right. Only once you find something you want to use, share, or just keep for future reference, you can copy it back up to the editor. This helps us, lets us iterate quickly in a carefree, non-reproducible way before finding something that's worth making reproducible. We can explore methods without needing to worry about architecture. The Jupyter Notebook approach mixes these two concerns. You end up with a long document full of half-discarded experiments, which invariably become dependent upon a nonlinear execution sequence that's impossible to reproduce. People don't tend to think or write code linearly, and we should embrace that instead of punishing it. Editing is a fundamental programming skill. Of course, you can edit in Jupyter, but it doesn't arise as naturally because the workflow doesn't require it. You can still do literate programming without notebooks. You can integrate code and documentation using alternative tools like Auto for creating articles, presentations, or books reproducibly. You can start from your report and then develop backwards, pulling in the analysis to the shape you need. For those that haven't tried it yet, I'd also recommend building packages in R for any non-trivial code, as you can use tools like Roxygen to do documentation-driven design. Before you write any code, start with a vignette explaining how to use it, which then helps to ensure that your syntax and semantics are intuitive, well-factored. You can then pull the implementation into existence. Likewise, RDoc lets you document each function with the examples that are executed as part of the package building process. This lets you do specification by example, along with your unit tests. By separating reproducible literate programming from ephemeral interactive exploration, you get the best of both worlds and avoid the risks of one contaminating the other. we can run the build process from scratch in an isolated environment, and we can't get ourselves twisted up with state mutation. If it's too slow to rebuild and threatening a fast feedback cycle, then we cache the chunks or grant intermediate results as it is. So in summary then, decay is physical inevitability, but maths is a term. Pure functions on a usable data are reproducible. Keep the core of your data flow as pure as possible. Extract side effects and inject dependencies explicitly. Use version control for code, models, and data. Automate workflows for continuous learning.
Thank you. I think this was is a great preparation for the next talk we have, right?
We can go to the direction of our packages.
Don't put the bar too high.
But thank you. Are there any questions or remarks from the audience?
Yes. I would start with a pretty stupid question. If I got you correct, you said the right CSV function would be a pure function. But on the other hand, if you have the same input to that function, you will always get the same output. So I can see the point for read CSV or for importing functions, but for writing, why would this not be a pure function?
Because the file system state is separate to the input function. So you give it a file path, but that isn't necessarily running on the same compute resource with the same disks attached.
Right. With a relative file path, that problem should be solved. So if you have something like write it in your current directory, there should always be one. So that would still be then reproducible handling.
I mean, possibly, maybe the directories don't exist. You know, the point is that the purpose of the function is to like write files out to a certain file handle, and it doesn't take responsibility for ensuring that that's going to be possible in the process that's running. And it's possible to explicitly configure that so that process only ever runs in a situation where that directory already exists and is available and writable to the process, and there's enough disk space, and all the other things that can go wrong when you try and write to disk. And that the write CSV function doesn't take responsibility for all of that stuff. It just takes responsibility for writing out bytes.
But no function ever takes responsibility that the input are constant. So you're just saying that the input changes, and it's true. Any pure function, if the input changes, will have a different behavior.
Sure, but the input that goes into the write CSV, the argument that goes into the write CSV function doesn't necessarily change. But the context in which it's run, if that changes, the function might work or it might not. And the point is about being aware that it's context dependent and being able to make that context reproducible if the function's not. So if you contrast it with something like plus, it doesn't matter where you run plus, it doesn't matter what disks are attached. It doesn't even matter which programming language you're using for the most part. Add something like floating point arrays and different interpretations. But the core of it, the result that comes back, shouldn't depend on all those things. But anything that does I/O has a dependency outside of its initial scope on the wider system.
But then even the plus function doesn't make sure that it gets the right data. So if you add plus between two words, you will still get an error message. So the function is checking something, but it can only check things once it is run. So it cannot test before it's actually doing something. And then write CSV, if that path doesn't exist, would give you an error message, just like plus would give you an error message if I would try to sum up our names.
Sure, but the point is that if you try and sum our names, it will always fail. If you try and sum 1 and 2, it will always succeed.
Yeah,
But if you try and write to data.csv, it won't always succeed.
Yeah, but the equivalent would be if you sum foo and bar, it will depend on what foo and bar really are.
Right, yeah.
So I think it comes back to the beginning of your talk, like you could create local order, but there is more global disorder. So what you are saying is that like we should try that the input are as local as possible.
Yeah.
So and that's the problem with the CSV is that it's defined outside the R system itself,
yeah.
while the foo or bar you would have an assignment like within your R system.
Yeah, and so if you've got something that's adding foo and bar, if that's just at the global context, global level, then yes, that's not reproducible. If you're within a function where you've defined two arguments, foo and bar, and you give that function names or the numbers, then that's then reproducible within that local scope. And the idea is to figure out where that scope is defined, and once you have it defined, you know that it's safe and reproducible within those bounds. And knowing, for example, that if you've got right CSV or something in there, it's side effecting, and that's no longer safe. So what I end up doing quite often is having my pipeline such that they only ever return data frames, and this is sort of like Fluent, it's actually the type style, in fact. And then the side effecting things then go into separate functions. So we'll only ever have data frames moving inside, and this thing is then composable and reorganizable, and all it really depends on is like, are the same columns with the same types and the same in place for moving stuff. And anything that's side effecting doesn't accidentally get mixed in and can be separated out, and then it's trivial to swap out a read CSV for read anything.
You took the example of LM on Broom, for instance.
What's
LM on Broom.
Yes, yeah.
You took this example. LM, what LM returns is a very huge list. So when you run your LM, so it calls a print method, which kind of process this list to just show you a side effect. But if the LM output would just be this little table, then you could not do anything with your LM else than seeing this little table. So we do need LM to return a huge, gigantic list. So in this context, you would argue that maybe you should just display the horrible list, and if we really want the table, we do call a specific function to see the table, or?
No, so LM, I'm thinking, I mean, certainly in ordinarily squares, it should be deterministic, right? So it should be
it is
reproducible, right? In itself, an unreal function, which is good. The summary method, though, so if you look at the inside that list, you can get to the bits that you need, but it's not particularly easily interpretable. So we'll often just reach the summary, because what LM prints out is just like, is it even print coefficients? Or it might actually be just the formula that with the coefficients, I can't remember, but it doesn't.
I get the coefficients, you get the intercept and the slope, that's the standard.
Well, but you also get the formula, you get the distribution of the residuals.
You don't get what's printed to screen when you call LM. So the fit result you can then store.
Yeah.
What's printed out to screen is a side effect at the same time. It doesn't include, for example, the p-values or standard errors of the.
It does, but it doesn't include many other things.
Exactly, and if you want to look at that as a table and say, what's the significance of the fit, and then you can call summary. The summary, you can't then use the result of that. And if you
Well, you can save summary to a variable.
Yeah.
I'm 100% sure I did it today.
Yeah, but then what is that variable?
That's a list, and then you can make use of that list. So doing logistic regression, if you want to get the p-values for your odds ratios, you get them from the summary in a convenient way. It's shitty names, and you can put summary then into Broom as well, but you can save summary into a variable, which means you don't have any side effect, just like LM. If you put LM into a variable, as you should, there will be no side effect, nothing will be printed. Only then printing that variable will give a side effect.
I mean, the general argument you're making is correct in many function playing with linear models anywhere, like which is the fact that you see on the screen on the what is stored is different, and sometimes what is actually displayed on the screen is created on the fly, and you cannot get it.
Yeah, exactly. I mean, the point isn't so much about the, I don't mean to like lampoon LM or anything, as the fact that when you print something out like that, if you can't capture it then, or if it's only done invisibly or something, then the side effect isn't really usable. But yeah, I mean, as long as you can get into the data, as long as that comes as an output function, and that's such to compose other functions.
So there's one remark by Barry, but we also had a question.
Yes, I want to ask about Jupyter notebooks. It's more a question about organizational things than technique or technical. Let's say you are new in a team and they use a lot of Jupyter notebooks. Is there an easy rule of thumb, like when to change everything and when not? Like, I don't know if you have an idea, but like let's say if you need this and that, redo everything. If you don't need to do this and that, just let it continue to stick with those Jupyter notebooks.
I mean, yeah, as tempting as it is to like say you just burn everything to the ground when you're in that situation, you know, that's not going to win any approval from your colleagues, and also it's a kind of a dangerous path to go down yourself, right? Completely right. So I would say instead to try and have like an incremental approach to reproducibility, and so the first thing would be like, if I restart the kernel, will this notebook run on the original computer, which doesn't always happen. Like I say, quite often people edit something and then move back up and have to redefine this thing and move back down, and then in the end they're using something up here that's defined over here because they executed it in a random order. So just running through one to make sure everything's in the right order, make sure each thing that's called depends on the things above it. Then moving to removing file paths that are only work on one person's machine, moving up to explicitly configuring it separately. Once you start to get into the mess of version control with notebooks, which is like finally there's some alternatives that don't store the state along with the book. There's a common syntax that you can use with things like VS Code that will give you those interactive cell and result values, but still leave you with a file where you can use NP converting things to give you files that then you can commit to version control and like see what's going on. And I think there's also like now notebook version control extensions that give you diffs and that sort of thing. But yeah, I would go through bit by bit, and eventually what I often end up doing is just running that NP convert to get a Python file or an R file back out, and then working on that, and you sort of start to free it then piece by piece. But it kind of depends what it's being used for. I mean, if people are using it as a sort of application, to run things interactively, and that's totally fine, of course. But once you then, which is generally the case, have to take that thing and put it into a pipeline, and bring engineering to the data science, then that's your like tolerance for non-reproducibility goes down quite quickly.
Packages are data with versions. So actually, when you design pure function, would you actually make as the input of each pure function the version of the package? Because if you have a function that is wrapping around functions that comes from packages, then this is in the global state.
Yeah, so at some point you need some encapsulation. You don't necessarily have to inject all dependencies. There's a pattern called state monad where you can basically take like a configuration and that gets passed into the functions and it's available. And you can get really carried away with this and like Haskell basically. But in a practical sense, probably what you want to do instead is dependency management. packages, which is to say that the package depends on explicit versions. And we're quite lucky in the R community because a lot of work goes into ensuring forward compatibility or roadmap compatibility. And reverse depends and all this sorts of things. CRAN is pretty on that going into the published package. Quite overhead in keeping everything up to date. But other languages are less lucky than that. If you try to maintain dependencies in Python or JavaScript. But the point is to have in your package, my package X, which this function assumes as a global state, depends on upstream package Y.
But there's in R, at least the way it was initially conceived, you were assumed to always use the latest version of all the packages, which is fine as long as no backward incompatibility is introduced. But with, for instance, tilers, that each update will introduce backward incompatibilities. And therefore, we're reaching this kind of problem that using the latest, like putting, because for instance, in your description file, when you write a package, very often what you do is you say, I want at least this version for this package. So you don't say, I want this version, you say, I want at least this version. But if, of course, then they introduce backward incompatibility, it means this requirement is no longer sufficient.
Yeah, and so you need to fix coordinates, and only when you have a mutable.
So you do that in R, you fix coordinate?
Not in R, but in pretty much every other language.
Yeah, I know.
Typically there'll be log files, and now you can use things like packrat to basically encapsulate your dependencies. But generally, if you're developing, we'll have open-ended. Open-ended dependencies, and then if it's released, then lock out to a specific version to ensure that it's fixed.
So I want to be Barry's messenger, because I also want to add something. So the first point that he made is he thinks that we should. So there are different contexts for reproducibility, and it's important to differentiate between the technical, pure reproducibility. We focused a lot on this today, and the scientific analysis on the other hand. This was the relative file path usually works, right? And so the right CSV is usually a good way to do, and in fact, it's far better than saving some R data workspace and reloading that magically when you open your RStudio session again. And I think so. Talking about the context of reproducibility is very important. So a little story from a book that we wrote. So I had a Mac machine, and the others had Windows machines, and we wrote a book together using R and Python code. So we did a lot of work in setting up environments, how this actually works, and we were super happy. Yeah, it was something that works, and we can share it with other people. So they can also just pull the Git repository, set up this environment. But of course, some obscure older Mac OS version doesn't have a Fortran compiler, and the reticulate package does not install. And we're like, how do you see this coming? So maybe my point is also the context of your reproducibility. Even if you talk about it, it might change over time, and then everything breaks that you have thought about before.
So just chronologically, the R data file would also very strongly saving your session state, and that's because you're basically packaging it with a notebook, and then your stream of consciousness will kind of be entering through your analysis system recorded for posterity. And good luck if you depend on something in there that isn't in your source code, because you'll never be able to reproduce it again. So yeah, definitely not to avoid that. In terms of the book, I think the goal should be to have a shared common programming environment, build environment for it. And each developer can basically take responsibility for sorting out their own system if they want to do something extra and use something faster or more convenient for them. But if you've got a central build system, then everyone can run it on there, and that's then the consensus. And ideally, you're then able to reproduce whatever that is on your local machine. So if you're running it in a Rocker container, for example, you can just get the tidyverse Rocker and all of your Quarto pipelines in there. And of course, there are you can install Python alongside it, and presumably now Quarto Python builds as well. That will support this sort of thing, and everybody can then run. They just need to take responsibility for getting Docker to work on their machine, and after that, you've got shared responsibility for everything that comes up.
I'm already happy that I got them to use version control. So using Docker is a bit too much. Can I add another question by Barry? What's the current best way to install a set of packages at a certain point in time? Checkpoint question mark. Is checkpoint a package itself?
Yeah,
or?
I think it is.
Ah.
I've not heard of checkpoint.
Yeah, it's RStudio. They're starting to cache packages on the.
Okay.
And I think checkpoint is one of the packages that they use to manage this.
So is it like an alternate R library? I think that's
They clone the crown every now and then.
Okay.
On that. There was also Microsoft was doing that at some point. MRAN.
Yeah.
I got an error today because some package version was not found on the MRAN server. So, but when I built it, actually when I sent it to the Docker container, it used the Docker image, then it pulled the correct version from the RStudio archive. So
Yeah. So think in terms of this here. You've got so I said that the version is composed of like a version identifier and a name location. So you hear implicitly here so this is the data set and this is the source for it. And you can imagine, going further up this identifier chain, you've got whatever the registry is for the package in the first place. So you could have the same name in two locations with different versions or different content. And the point is that it's sort of then scoped. Like this is universally unambiguous within S3, or rather within your user account. And S3, this is universally unambiguous. You need, a full URI, something on the web, locates it within the registry, whatever the name of the package is, and then it's coordinates. So anything that does that, and when you've got like replicas through, try that checkpoint, and I'll try that background briefly. I have to say, in R, I've not found this to be such a problem because compatibility is so good.
As long as you don't use it it's really different if you do.
So I have one package on Crank, and I put a required a per function in it that didn't quite do what I wanted. And there's I forget what it's called, but it goes down into a list. I put R on that. And because errors are stored as lists, it was going into errors and breaking what I wanted. So I wrote a version that basically just goes down as far as until it reaches an error and stuff. And wrote a test for it that was basically like, we only need this as long as the upstream version is breaking in this use case. And I'm going to mention his name, it's been an hour talking, we haven't yet. I got a pull request from Matthew Wickham to fix this because the per version upstream changed and didn't do this any longer. So his verse depends on per broke my package. So he created a PR to fix it. And that unheard of in the left pad example. Can you imagine other authors coming in and fixing your stuff? I think it's really lucky that we have that in the art community, especially from someone
But
who's busy.
If you build huge things that you don't share, so for instance, where I work, we have this big package with hundreds of functions, and systematically every tidyverse update something.
Okay, yeah.
Systematically, I know why, and I can. reticulate changes usually of behavior, the way they handle the conversion to list keeps changing. I have this problem as well. So,
but in this case, you would need to fix the specific version, right?
I try to keep with the flow. But it is no, it is problematic, and it's true that when you do installer packages for now, you at least in R itself you can't say this version because they don't want to guarantee that the particular version will work with particular version. They just test the latest state.
Yeah. I think there's probably a distinction between what you want as a workflow as a developer, which may be a bit more tolerant to being on code cache, with what you want for your reproducible builds as a consensus for your team, where you probably do want to have it locked down because you don't want to all simultaneously be solving the same problem or breaking other people's things because it's something completely unrelated. It may be that the primary experience of the form has meant that the tooling in the R is not as good for the latter. It's not something I've too much trouble with, but not working in that scale where there's so frequent breakage.
On the Rocker container themselves, are they kind of, if you take one that was 10 years old and you run it today in today's Docker, does it work?
So,
is it designed to be long-lasting, and so you could store like your?
So it had. That's probably more the case now. At the beginning, it was very, very volatile, and it would change regularly, and there would be still be problems between different systems. But I feel like that's sort of settled down. Whether that was 10 years ago or not, I don't know. In theory, you should be able to. Container should be portable, but it's not completely on-leaky abstraction. I wouldn't go into that.
Okay, any more questions, remarks?
Maybe just one more remark, leading again to next talk. So keeping things backward compatible is really something that is in itself quite annoying. So when you start writing functions, some of your argument names might be quite inconsistent and really shitty. So after a while, you figure out you really should undo this, but then you have the old argument name still as reference, even though you have the new ones. And so your list of arguments becomes longer. Then you have the old function name, then you have the new function name, and the old one is just a reference to the new. So on the one hand, you don't want to break anything, you want to stay backward compatible, but you don't want to run into the Windows problem. So like Windows, they try to be compatible to some extent, which means the whole operating system wasn't so shitty in the end because they try to keep everything working from the beginning. So sometimes I think making a cut and saying, okay, this will be deprecated, this definitely will be gone. And then if you use this, I'm using my own function, of course, then sometimes if it's no longer working, you have to go back and change that. If you give some message on how to change that because of incompatibilities, I think sometimes it makes sense to make that cut. So staying backward compatible forever would just mean your code is never evolving.
But you could also decide to create a new package once you really know what you want to do.
But then
when do we ever really know what you want?
That's why you have ggplot and ggplot2 and so forth.
Software's never finished, right?
Yeah.
There's a certain adaptability to that, and I think all you can do is be defensive towards it. So don't publish the whole of the API in the namespace. You only making available public things that you can use. Defensive guard clauses that if some assumption is changed between the versions, then don't throw up a warning and those sorts of things. But yeah, change is inevitable, and if you've got tests in place, then at least you've got some chance of catching it.
Okay, but I guess with this last remark, let's have one more round of applause for Robin. Thank you. and say good.